Very good morning, students. This is Dr. Eustace Russell, working as assistant professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So far, we are discussing the subject called Robot Dynamics and Control. The subject code of RA3601 under the regulation of 2021 for the 6th semester for the third year students. The last class we have seen the Unit 5 Force Control, impedance operators, and some of the few topics we have covered: torque relationships, static force, etc. Today our major topic we are going to cover in this force control tragedies and impedance operators. Why why it is the need for force control? Why position control is not enough? That is, traditional position control assumes the robot moves freely. However, many tasks involve contact with the environment. Example, surface polishing. A robot must maintain constant force. Plug-in hole assembly. Robot must regulate insertion force. Surgical robotics force must be carefully controlled to avoid tissue damage. Problem: small position errors can generate large contact forces. Solution: force control is the only solution. Concept of force control. What is force control? Force control aims to regulate the interaction force between the robot and the environment. Force error is given by EF is equal to Fd minus F. Fd equal to desired force. F equal to measured force. Objective EF tends to 0. Desired outcome: robot maintains the required contact force regardless of environmental variations. Example: robot pressing against a wall with 20 Newton force. Impedance operators. This already we have seen some of the basics in the previous lecture videos. Impedance operator defines the dynamic relationship between the force and the motion. In general form, we can write F equal to M double in differentiation of X plus B single differentiative plus Kx. M is inertia, B is damping, K is stiffness. Purpose is nothing but controls how the robot reacts to external forces. Interpretation: robot behaves like a virtual mass spring damper system. Then importance is nothing but a foundation of force control and impedance control. Classification of impedance operators based on dominant physical effect. Inertial impedance, that is represents resistance to acceleration, F equal to M X double dot, that is example heavy industrial manipulators. Damping impedance, that is represents resistance to velocity, F equal to B X dot, example shock absorbers. Stiffness impedance represents resistance to displacement, F equal to Kx, example elastic joints. Combined impedance used in practical robotic system, F equal to M X double dot plus B X dot plus Kx. Now in direct force system, we can see one block diagram. Input is there, force control, PID, then again exoskeleton, inverse dynamics. The top we have the human control is also there. This diagram illustrates a closed loop force control system. This closed loop system already we have seen in Unit 4 control manipulators. We have seen the closed loop system and open loop system also. It's used in an exoskeleton robot. Objective is to regulate the interaction force between human user and the exoskeleton while ensuring smooth and safe movement. Working principle: desired force Fd. Reference interaction force is provided. In this example, desired force is set to 0, meaning the exoskeleton should minimize the human motion. Force error calculation. Again followed by the direct force control. We have the force error calculation. Actual human robot interaction force F hour is compared with the desired force. Resulting force error is sent to the force controller. Force controller generates the required actuator torque, that is tau actuator, to reduce the force error, ensure comfortable interaction between the human and the exoskeleton. PID controller refines the control signal by reducing the position and the velocity errors, produces the control torque tau of PID. Then inverse dynamics compensation computes the gravity compensation torque, that is tau gravity, reduces the effort required to move the exoskeleton. Exoskeleton system is nothing but receives the combined torque command tau equal to tau of PID plus tau gravity. It produces the joint angle output theta. Human interaction feedback. Human applies forces to the exoskeleton. Interaction force is continuously measured and feedback to the controller. Then we have the indirect force control and force feedback control. Indirect force control, we have the principle. Principle is force is estimated from robot dynamics instead of measured directly. Our estimation, we are having tau equal to, that is transpose Jacobian into F. F can be calculated from measured joint torques. Features: no force sensor required, lower cost. Advantages: simpler hardware, reduced system cost. Disadvantages: lower accuracy, sensitive to model uncertainties. Application: industrial automation and material handling. Then force feedback control, we have that closed loop force control. Force error is nothing but EF is equal to FD minus F. Control law, U equal to KP FD minus F. Then working, that is measure force, compare with the desired force, compute force error, adjust actuator torque. These are the working one. Then we have the benefits of the force feedback control: continuous force regulation, improved robustness, better contact performance. Then industrial application, various industrial application we can have a glimpse in this slide. Assembly operation, first of all, peg-in hole insertion, record force, prevent part damage, surface finishing, grinding and polishing, record force, uniform surface quality. Then welding, maintain constant electrode pressure. Then medical robotics, protect delicate tissues. Human robot collaboration, safe interaction with humans. Here we can see the force control system having a various real-time application, industrial application, cutting by saw, peg-in hole task, and various multi-arm cooperation, manufacturing cells, deburring, everything we can see here. Kindly go through these industrial applications. Then overall summary of the today's lecture video. The main key concept is nothing but force control regulates robot environmental interaction. Evidence operators define force motion relationships. Three impedance components we have seen: inertia, damping, stiffness. And direct force control uses force sensors. Indirect force control estimates force from robot dynamics. Force control is essential for assembly, polishing, welding, and collaborative robotics. Impedance control overcomes many limitations of pure force control. So these are all summary what we have discussed in the today's class. These are the various references which I used to prepare this content. Kindly go through it. That is force control concept, Jacobian force mapping, force sensors, industrial assembly robots, polishing grinding robots, human robot collaboration, mechanical evidence, force control theory. Thank you students for your kind attention. Kindly subscribe the video, share this video to your friends. We will meet in the upcoming video, the last topic in unit 5. So all of you kindly go through the content. Thank you all.